Welcome back to day 2 of renal physiology with SPFD. We saw yesterday one of the functions of the kidneys was to regulate the body's pH. Today's lectures will discuss more of these kidney functions. Our kidneys are interesting structures. These two retroperitoneal organs are incredibly important to life. They serve to buffer the blood, regulate plasma composition, induce hormonal or systemic changes, and serve as an elimination mechanism. But before we can go on, we have to look at the macro and micro structures of the kidney, and just as we did with the cardiovascular system, we've got to learn how blood flows through the system. Blood enters via the renal artery, which is a branch of the abdominal aorta. Blood then goes into the afferent arteriole and then into the glomerulus. The glomerulus is a capillary bed where filtration occurs. We will come back to this. Next, blood flows out of the glomerulus via the efferent arteriole. This blood then continues into another capillary bed known as the vasa recta. This capillary bed is also called the peritubular capillaries. After this capillary bed, then blood will flow out of the kidneys and into the renal vein. This is going to be a pathway that you will need to learn and memorize as we will be working with this system over and over again. The afferent arteriole is responsible for delivering blood to the functional unit of the kidneys, known as the nephron. The efferent arteriole is responsible for taking the remainder of the blood flow that is not filtered and take it into the peritubular capillaries. These two places can be the action site for different drugs and hormones and can be affected by different disease states. For example, angiotensin II is a powerful vasoconstrictor within the body, but it also preferentially constricts the efferent arteriole. This comes into play when we want to talk about GFR, or glomerular filtration rate. Within Bowman's capsule, we want to think filtration. We should think of filtration at this capillary just like we did during the cardiovascular system. Think back to the lecture that I gave. The same rules apply. Water or hydrostatic pressure pushes, protein or onconic forces pull water. The difference is that here in the kidneys we are dealing with fenestrated capillaries along with a charged barrier. This membrane has slits in it that allows ions and small molecules to pass through, even water. However, large particles such as protein should not end up in the filtrate unless there is a disease state. Things that are filtered out of the capillary enter Bowman's space. We call this the filtered load. This is the start of urine production. Anything that enters this space will leave the body in the form of urine unless it is taken back up. This brings us to the concept of secretion versus reabsorption. We covered this too in the cardio section, but for completeness sake, let's refresh our memory. We should think about this from the perspective of the blood vessel. Secretion is movement of a substance from the blood vessel out. So in this case, secretion moves a substance from the blood vessel and into what will eventually become urine. Reabsorption is the movement into a blood vessel. Absorption really deals with the GI tract, so this is termed reabsorption. So if a substance is to be filtered at the glomerulus but never ended up in the urine, then we conclude that this substance was reabsorbed. These two actions occur at the peritubular capillaries. So anything that ends up in the urine was either filtered in the beginning or was secreted. This lends itself nicely to an equation that, and as you know, at SPFD we love making you memorize equations. So, excretion is equal to the filtered amount plus the secreted amount minus whatever was reabsorbed. These structures seem pretty important, so we need to make sure that they're working efficiently at all times. We should be able to test them in the clinic. And we have different tests to assess the kidney's function. We're going to start out with GFR. This is the glomerular filtration rate. This is the volume that enters Bowman's space per minute. Let's start with some normal values. We know that The normal GFR is about 100 milliliters per minute. And some textbooks have us at about 125 milliliters per minute. So if we were to track an item in the urine over time, then we can see how efficient our system was operating. Substances like inulin can be used to calculate the GFR. It is freely filtered and is neither reabsorbed nor secreted. We can also track kidney function by measuring the level of creatinine within our serum. This substance is a byproduct of muscle metabolism that remains largely unchanged when excreted in the urine. It does this primarily via filtration. So if we have high levels of creatinine in our blood, then we can conclude that there is a problem with our kidneys. Let's look at the table on the left. Plasma creatinine levels and GFR are inversely related, so low levels of creatinine correlate with a normal GFR. Conversely, a high creatinine correlates with a low GFR. These are not the only tests that we can order, and we will go over more in class. However, this should get you started and provide you with a framework with which to listen to the lecture. As always, email me if you have any questions, and I'm happy to go over any of the material. And I'm happy to hear any suggestion that you may have. See you all in lecture. Bye.